Yes, it will be talking about, and the title is long, but there are two keywords. Title, I forgot to thank organizers for inviting to give this talk. So this keyword is integrability and universality. And this conference is mostly about integrability, and I'm mostly interested in universality, but sometimes they meet together, happen together, and that's very interesting situation. It's not always happening, it's quite rare phenomena. I would say it's normally happening in the low dimensions. Say in statistical mechanics, almost all integrable models are two-dimensional, except maybe like Zavolodchikov's tetraeders model, but it's exotic. So, but when it happens, it's very nice. Now, what I mean by integrability? So, integrability means that there are certain systems which are, by some miraculous reasons, solutions or properties of solution can be studied explicitly. There are closed form expressions for the solutions, so some objects you're interested in. And that's extremely nice. But when you're in a situation when you perturb your system, and this miracle disappears, and there are no closed form expressions, and then you cannot say much about solutions of your system, say time one or something like that. But asymptotic properties, after you look at them asymptotically and rescale it, look at this from a certain zooming into it, are the same for integrable systems. Then it's universality, and that's make it even more interesting, the formula which you obtain explicitly in integrable systems. And again, it happens not always. Say, normally it's related to the action of what is called randomization transformation or randomization operator. You define certain randomization transformation in an infinite dimensional space of systems. And then you want to prove that under the action of this transformation, system converges to a certain fixed point, a certain universal behavior. And sometimes you can realize this program. This idea of utilization is extremely general, so general that it's almost philosophical. You can make precise statements, conjectures about what you're supposed to see. It's notoriously difficult to prove. So much so that, say, the proof of the convergence to conformal invariant limit for the Ising model, which is one particular model where miracle happens, it's a Field's medal of Stas-Smirnov. And you do something else, and you cannot prove anything. Now, it started in statistical mechanics. Then it was actually in statistical mechanics when it started. It took some time to understand that convergence to fixed point implies universality. It was realized in the 70s, and then it moved to dynamical systems in the works of Matthew Feigenbaum, Feigenbaum universality and other things. Now it's extended to other things, settings. And dynamical system, you can prove more things than in statistical mechanics. And today I will discuss a particular example, very general problem, I think very beautiful problem about random geometry. And it's called KPZ, Kadar-Parisi-Zhang. And there are two KPZ, people know that, experts. There is Nizhny Polyakov, Zabolotchikov, and Kadar-Parisi-Zhang. They are disconnected at the moment, both about random geometries. And it was even a meeting in the Field Institute in Toronto, which was called KPZ means KPZ. But I don't think meeting really happened there. So people were still kind of, connection was not very clearly. So people feel that there is probably some connection, but it's difficult to formulate what it is. But just to give example, before going to KPZ, just example, baby example of this randomization transformation, this is what is called central limit theorem, is that in probability theory. And it will be some probability in what I'm discussing, but it will be very soft. It's last talk of the conference, so everything will be very soft. So the problem is that you consider sums of independent random variables identically distributed. And you want to understand statistical behavior of this sum. So this is IID, independent identically distributed random variable. Now you add them, of course it will grow somehow, the size will grow. So it's pretty clear that if you consider second moment, you have to normalize the square root of n. And you want to study statistical behavior of such things. Now the fixed point is very easy to find, because if the distribution of the thing is normal distribution, Gaussian distribution with mean value 0 and variance 1, then we know that sums of independent Gaussians are Gaussians. So it will be Gaussian variance, which will be n divided by square 1. So this thing will have exactly the same probability distribution. For any n, limit will be the same. So this is integrable model. And it turns out that if you, under very mild conditions with probability distributions, if you do this procedure and n goes to infinity, this will converge to normal 0, 1 for almost every distribution which has variance. Variance exists, then convergence is happening. And that's the fixed point, this integrable part. And you can write the density, it's e to the minus x squared over 2 with a normalizing coefficient. But the interesting statement is universality. Now, universality was not realized immediately. It was Moivre-Laplace theorem, which just calculated combinatorially that it converges to Gaussian. It's a very nice exercise. Then the theory of characteristic functions and Fourier transform give you easy statement why it's convergent. But that's more or less what is going on. Now, what is rendition transformation here? Rendition transformation is the following. You take any probability distribution, you take sum of two things which are independent with the same probability distribution, then you get some probability distribution of the thing, you divide it by square root of 2. And that is transformation from one probability distribution to the image of it. And you want to find fixed point of it. And fixed point will be this Gaussian distribution. And then you can find stability of this fixed point. And it's easy to find eigenfunction for this transformation. They're given by Hermite polynomials. So you easily find that this is stable fixed point. And that's why everything converges to it. This is a baby example. It's easy to find spectrum. It's easy to prove convergence. But that might give you some idea what's going on. Now, this is introduction. Now, what is about KPZ? So KPZ is a phenomenon that is literally described, maybe even papers before, but normally people attributed to Kadar, Parisi, and Zhang. Parisi got Nobel Prize for a variety of his papers. That was not the main paper for which he got it. It was cited. But I think the main person in this paper concretely was Kadar rather than Parisi. Zhang was a student of Kadar. He came as a postdoc to Parisi. And then this paper, simple paper appeared.
Physicist.
Parisi did, all three physicists, yes. Parisi did a fantastic work about spin glasses, and that was completely different thing. Sherrington-Kilpatrick model, that was main source of his. Anyway, so the way they describe it is not how I describe it now. And
Which year was it, roughly?
It was middle of 80s, I think 87, something like that. I'll describe it differently. The phenomenon is extremely general. So you should consider two-dimensional plane, and you consider some random profile landscape on this plane. Some hills, some valleys, some mountains, or the one landscape. So how you can think about it, you have a function on a plane, and the graph of this function gives you this landscape. And then the problem you want to consider 2 points on the plane, A and B. And then you go to the landscape over these points, and you want to find geodesic connecting these 2 points. And you want to take these points very far from each other. So you want to find geodesic connecting these 2 points, so gamma A and B. And A and B will be far away. Kind of direction will be down for me, but it's not essential. It's just all directions are the same. You should assume something about your disorder, about your kind of random landscape. So it's natural to assume that it's translation invariant. That distribution, what you had here in other places, is the same. It's natural condition. You also should assume that it's pretty independent if things are far away from each other. So if you see some hills in America and in Asia, they're independently appearing and not related to each other. It's 2 natural assumptions, nothing more. And then the question you want to study is what will be the asymptotic behavior of the lengths of this geodesic? And what will be geometrical property of this geodesic? Now, I fixed 2 points of this thing. You can also play the game and you fix 1 point. And then you just prescribe that you end up at certain line. Not prescribing exactly that point. This is called point-to-point situation. This is point-to-line situation, but more or less of the same spirit. you still would have certain minimizing curve gamma. Endpoint is not prescribed here, and you're still interested in what is the length of it and what are the properties, some geometrical properties. So what about the length of this geodesic? And let me denote by L the Euclidean length, and this will be much larger than 1, goes to infinity. So it's easy statement in statistical mechanics that the length will be proportional to L. This is the realm of what is called subadditive ergodic theorem. It's an easy statement that if you take this length and divide it by L, it converges to a limit, a constant, which is not universal constant. It's not very interesting. And this constant is non-random. So for almost all realization of your profile, this constant will be the same if you fix probability distribution of your profile. So if you divide by L, it's not an integer, it converges to a constant. What you do in probability, you subtract the thing. You subtract this constant, which is non-random constant, which is limiting thing, but times L.
So I didn't understand. So what is the distance? So you take a random Riemannian metric in the plane, yes?
So I just create some graph of function. I consider some random
Graph of
over
function.
the plane.
Ah,
Yes.
yes. Okay.
All right.
What do you mean by
But you
geodesic?
can ask this question again. You
What
just
do- what-
calculate length. I mean, when you go
So-
to Arthur's
Using-
you go there.
Induced metric.
Yeah, yeah.
So there is metric.
Yeah, there is a metric, yeah, but I don't want to, at this point, I don't want to consider random Riemannian metric. Although it's a good question and probably can be answer will be the same. Now, the question is, what are the fluctuation of the thing? So previously we had fluctuation with the square root of the number of random variables. So here number of random variables is proportional to L, but fluctuation will not be square root of L. Fluctuation will be L to the 1/3. And it's one of the prediction of KPZ. They actually predicted this index 1/3. So this is a critical index. And it's manifestation of integrability that we know this number. Very often, this will be not a nice number. It will be not rational number. Here it's a rational number. That's manifestation of integrability. And then the main statement that if you divide by L to the 1/3, then distribution, it converges to some law. And this law is universal. And it's called Tracy-Widom law, which appears in the context of large random matrices, and it's related to integrability, it's related to Payne-Levy equation, and that's one of the reasons why I'm allowed to give this talk. And this Tracy-Widom law will be slightly, so the answer will be the same in both situations, but Tracy-Widom laws will be slightly different. So in this particular case, it will be Gaussian unitary ensemble Tracy-Widom law, and for this situation, it will be Tracy-Widom law of the Gaussian orthogonal ensemble. So meaning that if you think about random matrices, the random matrices complex random variables which are Hermitian, and here they're orthogonal, they're symmetric matrices. And so it's invariant unitary because it's invariant on the action of unitary multiplication by unitary matrix, and here orthogonal matrix. This is particular probability distribution. And maybe I'm not so much interested in the formula. I cannot write actually the formula, but I can write formula through the solution of Payne-Levy equation. So maybe I'll do it because otherwise it would be a little bit.
This is a result of KPZ?
It's not a result of KPZ. So in this generality, this result was never proved. But there is a zoo of models for which you can prove it. And these models correspond to particular distributions of disorder. And basically, most often you would live on a lattice rather than on a plane. And I would go to a lattice and everything will be concrete and kind of.
It's a conjecture, yeah?
It is a conjecture, yes. But it is a conjecture which you can kind of give, not maybe hand, but finger. That it's correct. Okay. Of course, you have to say more precisely what does it mean that correlation decay for the disorder and so on, but that is a kind of conjecture. In a reasonable situation, that would be true. Now, before maybe I write formula for Tracy-Widom law, I will say another law. So another law, what is geometrical properties I want to study? I want to see how far here I'll go away from the initial point. And here, since maybe I would look at the middle, how far I'm going here. So transversal fluctuations of your geodesic compared to the straight line, which will be on the line plane. So delta on L. And delta on L turns out to be order L to the 2/3. It's another critical index of Tracy Widdom of KPZ theory. This was also predictable KPZ, but then the fact that when L goes to infinity, distribution converges to universal law, which actually has no name. But it's some universal probability distribution, which will happen in all terms. If you normalize, you get universal statistics of that thing. Here and there. The statistics will be slightly different, but the scaling will be out of the third. Now,
Is this other universal law, does it also come from a Panevet equation?
no, it's not, can be described not, no, Tracy Widdom come from related. So let me just write it down. So for GOE, the probability distribution function is a function which, well, cumulative distribution function, goes from 0 to 1. Say, what is probability that something is less than X? And I would describe formula for GOE. There's a function of S, and this is equal to exponential over minus integral from S to infinity. And here you have X minus S squared, sorry, square X dx. And Q is the solution to Panevet 2 equation. X is equal to X, Q on X, plus 2 times cube X. And this particular solution, which is chosen, it's particular solution, which is chosen with the condition that we prescribe certain behavior plus infinity. So Q on X is asymptotic to any function on X when X goes to plus infinity. And any function is particular integral. And I would write a particular place. Area on X is equal to 1 over 5, integral from 0 to plus infinity, cosine t cube over 3 plus xt dt. So you can understand everything about behavior of the thing. Also to properties. If you differentiate the universe, you get density. And density will be decaying differently on plus infinity and minus infinity. One will be decaying like e to the minus s cube, another e to the minus s to the 3/2. So basically, you know everything. And
This is Tracy Widdom formula.
this is Tracy Widdom formula, yes.
And they derive it in
They derive it from random matrices. It happens that it also serves here. It's actually not very clear why it serves here, but what I'll describe, it has more structure than random matrices, because here I have lengths and geometrical properties, and there I have only, in random matrices, I only have eigenvalues, which is equivalent to the lengths. And we don't have geometrical object like minimizer, like geodetic. So it has more structure, that's why I think it's more relevant. So GOE will be similar formula, and this is the same as exponential over minus 1/2 integral from S to plus infinity, the same QX dx. And this is multiplied by F GOE S to the power 1/2. Anyway, it's just formula.
the same Q.
The same Q. Right, the same function Q. Okay, now, so it's extremely general statement. And I'm going to a lattice now to make it more precise. So on a lattice, you do the following. So instead of plane, I have Z2. 2 is essential. The problem can be described in any dimension, but then nobody knows anything about the behavior. And even physicists don't know it. So people will have different opinions.
And here also 2 is essential.
Significant.
Here 2 is essential also in
Yeah,
the continuous case.
The only thing which is not general here is dimension. Dimension must be 2. So Z2, that is like a 2, and then at every point of this, like now, I would also think that I have X now space, and I will be time. It doesn't matter the plane, but it will be convenient for me to think that there is a space direction and I direction, right? So I start time equal to 0, and then I have all the lattice points. And at every point here, it will be disordered lattice, what is called. So at every point xi, there is a random variable which depends on this point. And selection of these random variables is independent, identically distributed. So you have a lattice, at every point there is a random variable living, just a number.
So when you said that to make it more precise, that continuous problem, is it a well-defined problem with unknown answer, or is the
It
problem?
is well-defined problem is unknown.
So is it renormalizable,
So,
suitable?
but
Yes?
what you asked me, for example, how you define length and so on, now I'll define the length.
No, I mean like it's a two-dimensional Euclidean quantum field theory
No,
essentially.
it's not Euclidean quantum. There is nothing quantum here. Everything is classical.
Well, but yeah, but there is a random surface, yes? So
The surface,
and
but it's
this is-
just random surface. There's nothing, not everything random is quantum.
Random function of two variables.
What I said is an interesting question because I would say you can, so geodesic is a minimizer, right? It's a
Yes.
minimizer of the length. I can consider problem when I consider all possible connections and I would weight them proportional to e to the minus beta times their length. So that minimum length would have preference. So it will be positive temperature variant of the problem. And the scalings will be exactly the same and limiting law will be exactly the same. So it's an amazing situation where universality is so strong that for positive temperature, for zero temperature, you have the same scaling behavior. But I don't want, I would stay with temperature equal to zero temperature thing, so I will consider minimizers. So
Question, but the geodesic is not unique, you know, there are plenty of geodesics going from A to B.
no, they are not positive, it's the shortest one. The shortest connection.
Well, we're only taking maybe there are many shortest ones, but they have the same length.
Okay,
By definition.
let me just come here. So I think that you have this probability distribution. So at every point there is a random number. For example, Gaussian random variables. It's just an example.
X here is integer, so
X is integer and I is integer. So I start at certain point, say 0, 0, and then I go to nearest neighbors. And maybe I prescribe where I end up at time n, or I don't prescribe, it doesn't matter, but for every pass gamma, I would have action of this pass, which is just sum of these random variables alone visited by my pass. I just take some of them. And I want it to be smallest. Now, if the probability distribution is continuous, then this almost surely it will be just one pass which minimizes it. You cannot have two passes with the same length. And then you define this minimizer will be just what's called argmin. So it's a pass on which minimum realized. This expression. And the length which we're discussing will be that is a geometrical object, and the action of this pass is what was the length. And so the statement would be that if I subtract constant time L from here and divide it by L to the 1/3, I would converge to trace them either one or another, depending on which state will be. Now, to say the truth, I also have to multiply by some constant alpha, which is also not of interest because I want particular, otherwise there will be some scaling of trace. So I'm not putting this. And then also statement will be that this distance will be order L to the 2/3, so it will be delta divided by L to the 2/3, and it converges to universal. Now, as I said, there is a zoo of models where it's proved. For example, if this probability distribution is geometrical probability distribution, then it's proved. There are certain miracles happening for certain probability distributions. Now, it's also related to particle systems, but I'm not going into it. Universality problem is basically open. It is not much is known about. And so, in fact, it's a much more of universality you can say. Why would you start from one point? So the most glamorous form of this universal behavior will be the following. For example, that you start from all the points at the same time, using the same disorder. And you look at the connection of point which will be x n to the 2/3 with the point y n to the 2/3. 2/3 because I know that 2/3 is the right scaling here. L is n. The length is n. And then you consider all of these numbers depending on x and y, rescaled x and y. So time is, I now think that time is one. I kind of rescale time and rescale x and y, and I consider this optimal thing of a point, say from point x and to the third, point y and to the third at time n. I subtract constant time n and divide it by n to the 1/3. So to alpha, but I'm not right, we agreed not to write it. Now I have to compensate if these points are far away from each other. It turns out that compensation will be just non-random. I have to subtract this. And this thing will converge when it goes to infinity to a process which is called airy process, depending on the action y. And this will be double stationary. So you can move x by anything, y by anything, differently, the distribution will not change. And this is universal process, which describes, now it has correlations. Different things will correlate. That's everything here is universal, supposed to be, and in some models it's proven. It's one of the, you can do even more than that. You can even rescale time and take it for time n times s. That will depend, or say you take n time t here and n time s here, and then it will depend on 4 parameters, x, y, s, and t rescale time. That's a more glamorous form of this universality. But I'm not going here very strong. Now, the fact that I'm going to nearest neighbors is not essential. I can go to next nearest neighbor, or I can, different local behavior is not essential. On large scales, things will be universal. Now, the problem is to kind of understand this phenomenon. And
What is this A bar? Is it the length of
it is a sum of random numbers along the path. Is bar. Bar means it's a minimum of this overall. When I put bar, it's a minimizer, and this is action of minimizer. So the total. And what I said before, you can consider what is called directed polymers, consider all possible paths, and you consider probability distribution e to the minus beta, and then you put action of a particular path, divided by partition function, which depend on n. And this also will depend on n. And you consider this probability distribution on all paths. That's called directed polymers. Beta is a number, inverse temperature. And when n goes to infinity, the behavior will be very similar. So it turns out that this branch of paths will not behave like diffusive, going spreading around. They will be pretty concentrated, and distance where they will be order n to the third. And partition function will be of if you take logarithm of partition function, that plays the role of an. And then you have to construct constant time n, another constant, and divided by n to the 1/3, and it again will converge to the same Tracy-Widom law. So that's what precise statement was said. Now,
Just sorry, in terms of thinking about the continuum limit as well from this sort of discretization, as you would sort of increase your lattice density, one might reasonably worry that the sort of the thing you get out isn't smooth enough to have geodesics.
you can do this, but you can define thing directly on the it depends. It's just some people in community where I'm coming from, or where part of me coming from, people feel more comfortable living on the lattice.
No, but
Other communities, people would feel more comfortable living on the plane.
but that was also my question. The random surface is not very regular. So what is meant by geodesic?
No, if it depends on what random function you want to consider. So it's a graph of random function.
Right.
And it can be very regular. It can be differentiable, the surface.
So it depends.
It depends.
definition.
So you see, if it is not correlated on small distance, then it will be irregular.
Right.
But you can consider it correlated on small distance, but not correlated on large distances, and then it will be smooth.
Ah.
And then there is no problem.
And it doesn't depend much on what kind of random function you.
It doesn't matter. That's the beauty of this. It doesn't matter for any distribution. No, you have to be reasonable. So in probability theory, you don't want to have what is called heavy tails. So you want to have certain number of moments. Assume that normally people assume that this random variable should have 6 moments. But Gaussian would have infinitely many moments. So or you can consider that the compact support, so that it's not a good. But be reasonable. Because if moments, even in central limit theorem, if you don't have second moment, it is a area of stable loss, it's a different behavior. Okay, so now let me do a little bit of, I want to put it in a context maybe a little bit more general, even than what I considered before. And I want to do some kind of maybe dynamics here. So I want to look at this type of thing, but I'm going from all the points. And I want to look at the minimizing curve. Now it's the lattice or not lattice will not be essential. We draw pictures of the plane. So I will be starting from every point, and I would consider this minimizing going from this point. Now, it's actually, you can prove that you can consider infinitely long minimizers. Turns out that if n goes to infinity, minimizer will stabilize. So the geodesic will stabilize. So there is infinitely long minimizer. But it's even not essential. You can consider extremely long one and then consider big chunks of time here, which are much smaller, which are huge, but much smaller than that. It's up to you. But I would draw infinitely long things. And I start at time 0. And then they're infinitely long minimizers. And I would consider them at certain large time n. And then I will consider starting from every point here at time 2n, and so on. So it turns out that many of these minimizers would come together because they want to go kind of optimal paths. So what will happen is that you will see that many of them will come together, either to one point on the lattice or in a very short interval of the plane. And then there will be another interval which comes to another point. And this will be random. So it will be interval kind of coming to one point, another interval coming to this point, and so on. And the length of the thing will be order n to the third. That is a scale. And the length here will be also order n to the third. Order. It's a random number, order n to the third. So if you look at the map from here to here, I will call it transport map. You will see a monotone function because you have monotonicity. It's an important thing that minimizers cannot cross. If they meet, they go together. So if something goes to the left, it will stay for the left forever. That may be the same point. So if you look at the graph of the thing, so it will be piecewise constant map because the whole piece comes to one point. This is piecewise constant. So the graph would look more or less the following way. So it's a graph from this x to this y. And after I rescale them by n to the third. So they will be going along the diagonal, and it will be something like this. So it's a random curve like this, monotone, piecewise constant map. So I give this piecewise constant map T01, going from rescale time 0 to rescale time 1. And now I can start, there are very few points, but now I will start from all points here. Consider minimizers from all of them. So again, there are infinitely many of them, and record them in this position. It will be another less constant map. I call it T12. And I get the whole sequence of these maps.
It will be different from the first one.
They're random, yes. They're different realization, but they have the same distribution. What you'll get here, it would be a sequence of maps. All of them are piecewise constant, which is not very essential, but it's crucial they're monotone. So I have this map.
Independent. Yeah.
P1, 2, and so on. And this will be infinite sequence of maps. So what do we get? Stationary, meaning that they have the same distribution. Monotone. And piecewise constant, but that's less essential.
Independent also. Yeah.
They're not independent. Stationary, but not independent. If they would be independent, then the scaling will be square root of n.
But why are they not independent if they're related to
Ah.
disjoint pieces of
Yeah.
space?
Because they're infinitely long minimizers. So they know
Ah.
that they're past
yeah.
the same. If they will be just restricted to this strip and this strip, they will be independent.
Ah, yeah, yeah.
And if you will consider a sequence of independent maps, random map of this type, and you start to iterate them, they would scale like square root of number of them, not n to the 2/3. So it's because of correlation it's happening. And now, what will be my realization transformation, kind of its simple version? I would just go from here, iterating two of them, going from 0 to 2, from 2 to 4, and so on. So I go to 0, 1, 2, and then next one, and so on. So I take pairs of them together. And I rescale x, because x should be rescaled. And you can naturally define rescaling by fixing certain this code. For example, its t can be normalized by requiring that average value of the image of the origin square is equal to 1. It's normalization factor that the values of it. So you rescale to keep this property. And then you get probability diffusion. You have a transformation R acting from space of such sequences to also stationary sequences, also piecewise monotone, piecewise constant and monotone, and also with the same constant. And then you want to ask, what are the fixed points for this transformation? And the conjecture which we put forward is that it's enough to have monotonicity so that you converge to particular probability distribution in the limit. So if I apply Rn many times to particular stationary sequence, it converges to a fixed point. And m goes to infinity. And this fixed point will be universal, subject to some condition which I will describe in a moment. So that's a conjecture. So the idea is that why low dimensions is important? Because in low dimensions there are not enough space. You are very tight, and you cannot cross. And to adjust stationary sequence so that they will have prescribed scaling behavior is unique. Statistically, there is one statistics which is compatible with this type of picture. But you have to fix scaling. And here I have the following condition. What was KPZ? KPZ was saying that if I iterate the thing n times, apply it to 0, that this thing will be of the order of n to the 2/3. But nobody's told me that it should be n to the 2/3. It could be n to some alpha. And alpha can be anything between 0 and 1, but actually I would consider it between 1 and 1/2. There is an impact. And so conjecture is that if you have system which has, by some reason, has certain particular power law behavior when you iterate n of them, giving certain alpha, then all the system would converge to the same fixed point, which will be parameterized by alpha. For different alpha, it will have different fixed point. And n to the 3rd, alpha to the 3rd equal to 3rd is just particular fixed point of this thing. Here I'm discussing only geometry. Only this concentration points, which is geometry of this geodesic. I'm not asking about their length. It's another question, what is the length of them? And it's another question whether you can write a length associated to one of these fixed points. By physics and by consideration of the initial problem, I know that for alpha equal to 3rd, there is a length, there is a variational description of this geodesic, but for others it may not exist. And so the problem is split in two parts. There is a more general statement of geometrical universality, which is valid. I'm cautious here. I want to put it between 1/2 and 1. And I'll explain in a moment why. And another question is that suppose you know this fixed points geometrical, the question is, suppose you know this fixed point and suppose you know that they exist variational description. Then there is unique statistics of this description, which is compatible with these statistics. So kind of two type of thing. Maybe sometimes it doesn't exist, this variational description. You know, that this can be only one. And so I would concentrate a little bit on this and explain a little bit why I split here 1/2 and not the whole interval from 0 to 1. So maybe I would keep a particular description for alpha equal to 1/2. This is an easiest case. This case corresponds to independent maps, as you want. And then fixed point can be described explicitly. And again, there is a integrability there. Started by Alexei Baronsky and many other people. So how to describe this limiting behavior? How to describe this map? That's in sequence for alpha equal to 1/2. So I consider the process which is called coalescing Brownian motions. It was actually introduced by Richard Aratia in his thesis in the end of 70s. No connection to the problem. I'm considering this following object. You start from, you take a real line, and from every point of real line, you start independent Brownian motion. And then you play the following. If they meet, they go together. They coalesce. You have to walk a little bit to make it precise because they're a continuum of points and probably measurability question, but there are continuum of them, you have to settle, but it can be done. It was done in this variety. So what you will see that after every finite time tau, out of this continuum of points, you will have just discrete set of points reached this time, and all the rest will coalesce by that time. Because
So Brownian motion on the line.
no, Brownian motion in time. The only line, yeah. You just so
So-
you start Brownian motion, and this is a Wiggly function of time.
But the space is a line.
Yeah, the space is a line, yes. That's why they meet all together. Right. And because the Wiggly Hölder exponent 1/2 for Brownian motion, they would intersect a lot. And so you will have here discrete set of points, random set of points, depending on what the situation. And this, they will not accumulate anyway. It's discrete set of points. And then you have here intervals, which ended up at this point, and then interval which ended up at that point, and so on. And so if you consider map from here to here, it was exactly the map of a type we consider, piecewise constant monotone map. And if you take tau equal to 1, that would be this T01 map. And the next map is independent because Brownian motion doesn't have memory. And then next independent cell. And because of the exact scaling invariance of Brownian motions, it's obvious that if you take this sequence and rescale it by square root of 2, you get the same thing. That's obviously what this map will be fixed. Independent sequence of this map will be fixed point for this transmission transformation. Now, what Zaboronsky and others did, you can ask a question. So what you can describe it by this map, but you can describe it by this point field. Then the question, what are the correlation functions of this point field? And they can be studied in this case. And it turns out that many of these correlations are expressed through Pfaffian. When you write metrics, so for example, you want to say, look at this thing and you consider it like n intervals. And you ask, what is the probability that there are no points in all these n intervals, that these are empty? And then you write 2n by 2n matrix, which would have Gaussian kernels as a matrix elements, and Pfaffian of this will give you this probability that they're empty. So it's a Pfaffian process. It can be, so there is certain integrability here for this particular case. Nobody knows whether this integrability will carry out for 2/3. So not much known about probability distribution here. All right. And so maybe I would say a couple of things about the following that so that's coalescing Brownian motions. That's classical object. It's easy to study, relatively easy. Now suppose you want to get, suppose you don't know anything about KPZ and you want to get another alpha. So how to construct sequence of stationary maps with certain scaling behavior? Actually, it's a very non-trivial problem. And it's how you would do it. And so the method to do it is slightly more complicated. So you have to consider coalescing fraction of Brownian moment. Now, even probabilists dislike fraction of Brownian motions. They dislike it because they're Gaussian processes. They have stationary increments like in Brownian motion, but they're dependent. So it's not Markovian. So your past remember your future remember the past. But I will give you an idea of what it is. So it's a Gaussian process, and it's called Brownian with H called Hertz exponent. And this Hertz exponent is between 0 and 1. And this is a process which the variance of the thing behave like not like T for Brownian motion, but T in power plus 2H.
So h to the 1/2 is Brown usual.
But H to the 1/2 is the Brownian motion. And when H is greater than 1/2, it's what's called positively correlated. So you want to mimic what you did in the past. And when H is less than 1/2, it's negatively correlated. You don't want to mimic what you did in the past. You want kind of to do opposite.
The Brownian motion can be thought of as having density exponential of minus integral of derivative squared.
Correct.
And can you see if I take derivative to power like 1 over h, then is it the same?
Well, actually, there is a simple description of this process. It's going back to Paul Lévy. Paul Lévy basically introduced it in 53, but not exactly the same way. And in his case, he didn't have stationary increments. But if you take limit of what he did, and it was done by Mandelbrot and Ness, and Mandelbrot was a student of Paul Lévy, and he introduced in 60s, and everybody cited Mandelbrot and Ness, but it's a little kind of something built up over what Paul Lévy did. So the way to write it, you can write it as the following thing. You can write it as an integral from 0 to t, and here you have t minus s in power h dws, where this is a normal Brownian motion. So you take stochastic integral, but the integrand is and this will not, since you start from 0, that's what Paul Lévy did. Increments are not stationary, but if you run it for a long time, then increment will be stationary. So it's just a subtract. So Mandelbrot started from minus infinity, and that's the whole thing. Everybody cite Mandelbrot and Ness, but it's Paul Lévy. And this gives you a lot of control of what's going on because this is Markovian. Now, there's another beautiful thing how to describe this process as a limit of random walks. And that was done by Scott Sheffield and Alan Hammond 50 years ago. They did it only for h between 1/2 and 1. And that's why I want to get between 1/2 and 1, not from 0 to 1/2. So they do the following. So you want to build up random walk. Normally, random walk means that you want to decide to go to the right and to the left. So they do it with probability 1/2. This is a standard, simple, symmetric random walk. And here you do the following. You come to a point, you don't know what to do. And then you sample some point in the past. So some time in the past. You sample it with some probability distribution has power law of the sampling, and then you see what you did there. If you went to the right, you go to the right. If you went to the left, you go to the left. And you continue doing it. Now, in reality, you have to start in minus infinity again. So basically what you do, for every time you take parent. I have some time. You have parent according to sampling. And so you have these arcs on the time, and it turns out that it will be infinitely many clusters. And for every cluster, you decide plus or minus 1. And that in the limit will produce this thing. Anyway, this fractional Brownian motion has this type of behavior. And that is a way to produce fixed point for other alphas. So you can coalesce in fractional Brownian motion. Now that's a problem. Because again, you want to start from every point independent fractional Brownian motion, particular h. But when they meet, you have to decide which one is continuous, because they remember the past. And there are different strategies. The best strategy is just to toss a coin and to decide which one is continuous. And then you can construct this process of coalescing fractional Brownian motions. And they will be also colliding. So it will be similar thing, but statistically it will be different. and will depend on our age. But that will produce you just one map of this sequence. Previously, it was not a problem because next map was independent. Here it will be dependent, otherwise you will not get non-trivial age. So you have to produce other maps, and that is what is called coalescing. It's called Brownian web. So now you are starting not from every point, but from every point of x and time. From every point of x time, space and time, you start Brownian motion. And if they collide, they go together. And the rule is that if the older one meet with younger one, always older one wins. I like this rule. and for Brownian again, it doesn't matter. But you can construct, and then you have maps order from here to here, from here to here, and so on, and they will be correlated. Now, the paths which survive will not be any more fractional Brownian motion, because the fact that it survived for a long time changes its statistics. Conditional that it survived, it means the statistics was not important. And so by doing that, you can construct this fixed point. Now, we don't know how to prove that this fixed point is stable. We don't know how to show that you have convergence to these fixed points. But we have numerical evidence that if I take 3 people to the third, coalescing Brownian motions, statistics is the same as for what is called last passage percolation problem, which is KPZ. So numerically, we see that by all statistical tests, they look very, very similar. But that's not a proof. Proof is not available at the moment, but there is a kind of some support for this conjecture we have. So that's very much work in progress. I should mention that there is a very nice paper which was written by Valent Virak and his co-authors. They call it random landscape. And they're starting, they started geodesics, but they study this statistical geodesics starting from all different points. And using exactly solvable models, but again, assume that everything will be universal, and there are nice papers describing that. Nobody would predict that coalescent fractional Brownian motion would be the same universality class as KPZ. We believe it's true, but Virak doesn't believe in it. So I think a little bit of a open problem, but there are very interesting problem here, and I believe there is I believe that not only integrable cases alpha equal to 1/2. I think that other cases will also carry a lot of integrability, especially because we know that for alpha equal to 1/3, there is a lot of integrability. So there is a lot of room for looking at the integrable behavior for different alphas, and that is I hope you can describe the flavor of this subject of KPZ. And now I want to finish with one slide, which I prepared, but we have only screen, right?
Yes.
It was a discussion who is the first, who is the second, who meets Sasha. This is not the first time we met. Can you recognize Sasha?
The one with mustache.
The one with mustache with a little bit more hair than now is me. And the one with a tie is Sasha. Now, we're in Khanin, Central Asia, in Uzbekistan. It's a conference in Kumishkan. It's a summer school in the conference in Kumishkan. So there is no meetings. We are kind of vacation time. I mean, it's free time. We still wear jackets. Time changed. The dress code changed. Now it's completely different dress
It
code.
is 1970s.
It is now, it's 80s. It's like maybe 83, something like that. And that is our friend, and also from our, what Sergei discussed from our time at Moscow State. Mukadas Misarov, he's in Kazan, the same place where Lobachevsky geometry was developed. This is another friend, Andrei Goldberg. And we're enjoying fantastic Central Asia melons. And they're really fantastic, and they're huge, like that. They call them torpedo. They do look like torpedo. And this is some Middle Asian soup. I think it's some lagman or something. But that was the proof that we were young sometime ago, and also the proof that I don't know. I like this picture. I found it, okay.
Thank you very much.
Before I take questions, if there are any, my sad duty is to thank the organizers. Thank you very much. It was